August 1st, 2025, 4:30 in the morning, Hawaii time. The Atlas telescope, scanning the constellation Virgo like it does every clear night, registers something. A faint smudge of light, moving, not fast, not dramatic, just there, where it wasn't before. The automated system flags it, sends an alert. Within an hour, a human reviews the data. Within 4 hours, three more telescopes confirm the observation. And within 72 hours, after orbital calculations are run and checked and run again, the announcement goes out. We have a visitor, not from the outer solar system, not from the Kuiper Belt or the Oort cloud, from beyond. The third confirmed interstellar object in human history has just entered our cosmic neighborhood, and for the first time since 2019, the world stops to look up. They call it 3i Atlas. Simple. Clinical. But behind that designation sits a reality most people don't fully grasp. This thing, it came from another star system. It traveled for millions of years through the cold, empty dark between suns. And somehow, against odds that make lottery wins look common, it wandered into our tiny corner of space. For a few weeks, everyone celebrates. Scientists, media outlets, space enthusiasts posting animations of its trajectory across social media. The discovery is everywhere. Press conferences, news segments, headlines proclaiming humanity's newest cosmic guest. But while the world marvels at the discovery itself, a handful of astronomers are staring at their screens in quiet confusion, because something about 3i Atlas doesn't add up. And the more they look, the less sense it makes. Let me take you back to 2017 for a moment. October 19th. A telescope in Hawaii detects an object moving fast through the inner solar system. Really fast. Too fast to be bound to the sun. They name it Oumuamua, Hawaiian for scout or messenger. And after weeks of observation and orbital analysis, the confirmation comes. This object didn't belong to us. It came from interstellar space, swung past the sun, and left forever. The first interstellar visitor ever confirmed. It was strange, elongated, cigar-shaped based on how its brightness changed as it rotated. It showed non-gravitational acceleration, meaning it sped up slightly in ways gravity alone couldn't explain. And it reflected light oddly, more like bare rock than ice. Scientists debated. Some said it was outgassing, invisible jets of gas pushing it along. Others weren't so sure. One researcher even suggested it might be artificial, a light sail from another civilization. That idea got laughed at. Publicly, at least. But privately? Astronomers started asking different questions, started realizing how little we actually know about what drifts between the stars. Then in 2019, lightning struck twice. A man named Gennady Borisov, observing from Crimea with a telescope he built himself, spotted another interstellar visitor. They named it 2i Borisov in his honor. This one behaved more like a comet. It had a coma, a tail, outgassing activity. It looked familiar, explainable, but even 2i Borisov carried chemistry that didn't quite match our solar system's comets. Carbon dioxide ratios that were inverted. Compositions that whispered of alien stellar environments. 2 interstellar objects in 2 years. And now, 6 years later, we have number 3. 3i Atlas. The press releases are polished, professional. They talk about orbital eccentricity, hyperbolic trajectories, scientific opportunities. They emphasize how rare this is, how lucky we are to witness it. And they're right. This is incredible. But there's something those press releases don't mention. Something the scientists noticed within the first week of observations. Something that doesn't fit any comet model we've ever built. Dr. Elena Vasquez sits in front of her monitor at the Mauna Kea Observatory, pulling up the latest spectroscopic data. She's been studying comets for 15 years, knows their signatures by heart, knows what ice looks like when sunlight hits it, knows how dust reflects across different wavelengths. She knows what normal looks like. This isn't it. The albedo, the measure of how much light 3i Atlas reflects, is wrong. Comets are typically dark, dirty snowballs as the saying goes. Their surfaces are coated with dust, organics, carbon-rich materials that absorb most of the light hitting them. They reflect maybe 4 to 6% of incoming sunlight. 3i Atlas is reflecting 11%. That might not sound like much, a few percentage points. But in astronomy, small differences matter. They tell you what something is made of, how old it is, where it came from. An 11% albedo suggests a surface that's cleaner, smoother, less dusty than it should be. Dr. Vasquez runs the numbers again, checks the calibration, looks for instrument errors. Nothing. The data holds. She emails a colleague in Chile. Are you seeing this too? The reply comes 3 hours later. One word. Yes. They're not the only ones noticing. At the European Southern Observatory, a team analyzing high-resolution images spots another oddity. The way light scatters off 3i Atlas doesn't match standard models for icy surfaces. There's a uniformity to the reflection, a smoothness that feels almost polished. One researcher jokes, half serious, that it looks machined. No one laughs. Because here's the thing about interstellar objects. They travel through space for millions of years. They get pitted by micrometeorites, coated with interstellar dust, weathered by cosmic radiation. They should look rough, chaotic, textured. 3i Atlas looks clean. And that's just the light. Then there's the temperature. Infrared observations begin a week after discovery. Standard procedure. You point an infrared telescope at an object, measure the heat it's radiating, and it tells you about its size, composition, and thermal properties. Comets are cold. When they're far from the sun, beyond Jupiter's orbit, they sit at temperatures barely above the cosmic background, around 50 to 70 Kelvin. That's negative 370 degrees Fahrenheit, frozen solid. 3i Atlas on August 10th sits at about 5 astronomical units from the sun. Just beyond Jupiter's orbit, it should be reading around 65 Kelvin, give or take. It's reading 67 Kelvin, 2 degrees warmer. The astronomer reviewing the data assumes it's an error, recalibrates, checks the atmospheric correction, runs the measurement again. 67 Kelvin. He calls over his supervisor. They look at the data together in silence. That's odd, the supervisor says quietly. Because 2 degrees at these temperatures isn't noise. It's real, measurable, significant. Something is generating heat. Maybe it's residual warmth from when the object was closer to whatever star it came from. Except it's been traveling through interstellar space for hundreds of thousands, maybe millions of years. Any internal heat should have radiated away long ago. Maybe it's radioactive decay. Some isotopes in the nucleus breaking down, releasing energy. Except the amount of radioactive material you'd need to produce that excess heat would make the object glow faintly in other wavelengths. And it doesn't. Maybe it's outgassing, sublimating ice-releasing energy, except the object isn't showing any coma activity yet. No gas, no tail, nothing. The heat is there, subtle but measurable, and no one can explain where it's coming from. By August 20th, the celebrations have mostly faded. The initial excitement has settled into routine observation. Universities issue statements, research proposals get written, telescope time gets allocated. 3i Atlas becomes a project, a data stream, a series of measurements to be cataloged and analyzed over the coming months. But in labs and observatories across the world, a handful of scientists are passing quiet emails back and forth. Subject lines like, albedo anomaly, thoughts, or thermal excess still present, any theories? No one wants to overreact. No one wants to be the person who cries anomaly and gets it wrong. Careers have been damaged by less, so they stay cautious, professional. They talk about unusual characteristics and deviations from standard models. They don't use words like artificial or designed. Not yet. But the thoughts are there, unspoken, hovering in the background like static. Because when you've studied rocks and ice for your entire career, when you've seen thousands of comets and asteroids and know their behaviors by heart, you develop an instinct. You can feel when something is off, and 3i Atlas feels off. Dr. Vasquez sits in her office late one night, staring at the light curve data projected on her screen. The way brightness changes as the object rotates. It's too smooth, too regular. Natural objects tumble, they wobble. Their light curves have bumps and irregularities because their shapes are chaotic, their surfaces uneven. This light curve looks almost engineered. She closes the laptop, rubs her eyes, tells herself she's seeing patterns where none exist, that she's been working too many hours, that 3i Atlas is just a comet with weird composition and her imagination is running wild. But as she drives home through the empty pre-dawn streets, she can't shake the feeling. The feeling that something out there, drifting through Virgo, past Jupiter, heading toward the sun, is not what it appears to be. The world doesn't know yet. The news has moved on. The headlines have shifted to other stories. 3i Atlas is still mentioned occasionally, a footnote in astronomy blogs, a curiosity for space enthusiasts. But it's no longer front-page news. Which is probably for the best. Because if people knew what a few dozen astronomers are quietly noticing, if they understood the implications of light reflecting just a little too uniformly, of temperatures running just a few degrees too warm, the questions would start. Questions no one is ready to answer. Not because the answers don't exist, but because the answers might be something we're not prepared to hear. For now, 3i Atlas continues its journey inward, silent, distant, unremarkable to anyone not looking closely. But the measurements continue. The data accumulates, the anomalies persist, and in observatories across 4 continents, scientists keep watching. waiting for the object to do something predictable, something that fits the models, something that makes sense, waiting for the strangeness to resolve into normalcy. But as August turns to August and August fades into September, the strangeness doesn't fade. It deepens. And the question that no one wants to ask out loud starts to take shape. What if this isn't just a comet? What if the third visitor is something else entirely? October 9th, 2025, 3 months after discovery. 3i Atlas is now closing in on perihelion, the closest point in its journey around the Sun. In 6 days, it will swing past our star at a distance of about 0.8 astronomical units, closer than Earth orbits, before accelerating back out into deep space forever. This is the moment astronomers have been waiting for, because when interstellar objects get close to the Sun, they wake up. The heat triggers activity. Ice sublimates into gas. Dust gets released. Tails form. And all of that activity gives scientists a chance to study what these visitors are actually made of. It's the best window we'll ever get. Observatories around the world have allocated time. Telescopes in Hawaii, Chile, South Africa, the Canary Islands, Spain. Every clear night, instruments point toward the same patch of sky, collecting photons, measuring brightness, tracking how the object changes as it heats up. The data streams in constantly. Terabytes of information. Light curves showing how bright 3i Atlas appears over time. Spectra revealing its chemical composition. Thermal readings tracking temperature changes. Most of it looks normal. Expected. But buried in that flood of data, something else is happening. Something no one is looking for. Something that will take weeks to notice, and once noticed, will be impossible to ignore. Dr. Kenji Nakamura sits in the control room at the Subaru telescope on Mauna Kea, reviewing the previous night's observations. It's early morning. The sun hasn't risen yet. Outside, the summit is still dark, stars fading as twilight approaches. On his screen, a graph plots the brightness of 3i Atlas over the past 8 hours. The line rises and falls gently, showing how the object gets slightly brighter and dimmer as it rotates. This is normal. All irregular objects do this. One side reflects more light than another. As it spins, brightness changes. But something about this curve bothers him. He zooms in, adjusts the scale. There's a bump. A small spike in brightness around hour 3, barely noticeable. Well within normal variation. He almost dismisses it. But then he sees another spike. Around hour 6, and a third. Hour 9. He sits back, stares at the screen. Maybe it's noise. Atmospheric turbulence. A passing cloud briefly affecting the measurement. These things happen. You learn to filter them out. But the spikes are evenly spaced. Too evenly. He makes a note. Flags the data for follow-up. Moves on to other tasks. He doesn't know it yet, but 3,000 miles away, another astronomer is looking at the exact same pattern. Dr. Sofia Ramirez works at the European Southern Observatory in Chile. She's been tracking 3i Atlas since early October, running photometric observations every clear night. On October 24th, reviewing data from the night before, she notices something odd. A brightness spike, small, repeating. She checks her calibration, reviews the atmospheric correction, runs the data through her pipeline again. The spikes remain. She pulls up observations from 3 nights earlier. The spikes are there too. Same spacing, same duration. Her first thought, instrumental artifact. Something glitching in the camera. A processing error. She emails the observatory's technical team, describes what she's seeing, asks if there were any known issues with the instrument. The reply comes back within an hour. No known issues. Equipment functioning normally. She frowns, pulls up a wider dataset. 2 weeks of observations. And there they are, repeating every few hours. Small bursts of brightness like the object is briefly flaring and then returning to normal. She measures the intervals. 11.3 hours. Every 11.3 hours, 3i Atlas gets slightly brighter. Not much. Maybe 3 to 4%, but measurably, consistently. And the brightening lasts exactly 47 seconds, every single time. She sits very still. Because here's what she knows about rotating objects. When a comet or asteroid spins, its brightness changes gradually as different surfaces come into view. The light curve is smooth, sinusoidal, predictable. What she's looking at isn't smooth. It's a pulse, sharp, distinct, repeating, like a heartbeat. By October 13th, observatories on 3 continents have flagged the same anomaly. Hawaii, Chile, South Africa. Each team initially thinks it's a local issue, equipment error, data corruption, something unique to their instrument or their location. But when Dr. Ramirez mentions it casually in an email to a colleague in Hawaii, the reply stops her cold. We're seeing it too. Within hours, a small group of astronomers is sharing data privately, comparing observations, cross-referencing measurements. The pattern is consistent. No matter where you observe from, no matter what telescope you use, the pulses are there. every 11.3 hours, lasting 47 seconds, without fail. Dr. Nakamura in Hawaii calculates the exact timing of the pulses over a 10-day period. They're precise to within a fraction of a second. No drift, no variation. That shouldn't be possible, because space is chaotic. Objects tumble. Their rotation rates change slightly due to outgassing or tidal forces. Even the most stable asteroids show tiny variations over time. This isn't varying. It's locked. Stable. Exact. Like something is controlling it. On October 15th, an amateur astronomer named Diego Torres, observing from his backyard in rural Chile with a modest 14-inch telescope, posts something on an astronomy forum. He's been tracking 3i Atlas for weeks, posting his observations, sharing light curves with other amateurs. He's not a professional, doesn't work at an observatory, just a man who loves the sky and spends his nights capturing whatever he can. But Diego has good equipment, and he's meticulous. His post is titled, "Anyone else seeing this pulse pattern in 3i Atlas?" He includes a graph. His own data collected over 12 nights. And there it is. The pattern. Clear as daylight. One professional astronomer sees the post. Then another. Within a day, the thread has 50 replies. People sharing their own observations. Confirming the pattern. Asking questions. Someone suggests comparing data from different observatories to see if the timing matches. Diego volunteers. He downloads publicly available data from the Atlas survey in Hawaii, photometry from South Africa, and recent observations from Spain. He overlays them, aligns the timestamps, and when the graphs stack on top of each other, when the data from 4 different locations, 4 different instruments, 4 different latitudes comes together, the pulses line up perfectly. Not close, not approximately, perfectly. The exact same brightening, at the exact same intervals. Synchronized across the globe. Diego stares at his screen for a long time. Then he types a single sentence in the forum. This isn't instrumental error. By early November, the pattern is undeniable. The private emails between professionals turn into calls. Conference rooms fill with scientists reviewing data, running simulations, arguing theories, because every natural explanation they try doesn't fit. Rotation? Objects don't pulse when they rotate. They brighten and dim smoothly as different sides face the sun. And even if an object had a highly reflective spot on one side, you wouldn't get these sharp, brief spikes. You'd get broader, gradual changes. Outgassing? When comets release jets of gas or dust, brightness changes are erratic. Unpredictable. Tied to solar heating. They don't repeat on a precise schedule like clockwork. Tumbling? Chaotic rotation could create complex light curves, but not this. Not something this regular. Tumbling objects vary. They wobble. They don't pulse every 11.3 hours with 47-second precision. So what's left? Dr. Vasquez, the astronomer who first noticed the albedo anomaly back in August, joins a video call with colleagues in Chile and South Africa. What if it's internal? Someone suggests. What if there's a hotspot inside the nucleus, rotating into view periodically? Then why 47 seconds? Another voice challenges. Why so brief? And why hasn't the interval changed at all? Objects lose rotational energy. They slow down. This hasn't changed by even a tenth of a second in 3 weeks. Silence on the call. Dr. Vasquez speaks carefully. What if it's not rotational at all? What if something inside is activating? The word hangs in the air. Activating. No one responds immediately, because that word implies intention. Mechanism, purpose. And natural objects don't have purpose. On November 4th, a researcher at MIT runs a statistical analysis. She takes the pulse data, all of it, every observation from every telescope, and runs it through pattern recognition algorithms designed to detect periodicity in noisy signals. The algorithm confirms what everyone already suspects. The pattern is real, non-random, statistically significant beyond any doubt. But then the algorithm flags something else, something no one has noticed yet. The brightness of each pulse is increasing. Not by much, fractions of a percent, but measurably, consistently, each pulse is slightly brighter than the one before. She checks the calculation, runs it again. The trend holds. 3i Atlas isn't just pulsing, it's getting stronger. She sends the finding to Dr. Vasquez with a short note. It's ramping up. Dr. Vasquez reads the email 3 times, then she pulls up the thermal data. Because if the pulses are getting brighter, and if this is tied to internal heat like she suspects, she finds the Alfredo 100 correlation immediately. Every pulse coincides with a thermal spike. Deep inside the nucleus, something is generating heat, releasing energy, and that energy is making the surface briefly brighter, like a light bulb dimming and brightening on a cycle. But the heat signature isn't spreading evenly, it's concentrated, Localized, coming from a specific point within the object. She measures the depth, estimates the source location. Whatever is generating this energy sits about 50 meters below the surface, shielded, protected, deep enough that external sensors can barely detect it, deep enough that it's not an accident. She sits back in her chair, closes her eyes, because she spent 20 years studying rocks and ice. She knows what comets do. She knows their chaos, their randomness, their beautiful lack of structure. And this isn't chaos. This is precision. On November 3rd, a small group of astronomers holds a private meeting. No press, no announcements, just 15 people on a secure video call. They review everything. The albedo, the temperature anomaly, the pulses, the thermal spikes, the increasing brightness. One by one, they go through every natural explanation they can think of, and one by one, those explanations fail to account for what they're seeing. Someone finally says it, the question everyone's been avoiding. What if this object is artificial? No one laughs, no one dismisses it, because by now they've all thought it, privately. In the quiet moments between observations, in the late nights reviewing data, they've all considered the possibility, and none of them can prove it wrong. Dr. Nakamura speaks carefully. We need more data. We need to understand what happens at perihelion. If this is some kind of signal, if something inside is transmitting... He trails off. Dr. Ramirez finishes the thought. Then we need to know what it's saying. The call ends. No conclusions, no announcements. Just agreement. Keep watching. Keep measuring. Keep silent. Because if they're wrong, if this turns out to be some bizarre natural phenomenon they don't understand yet, the last thing they need is global panic over an artificial alien probe that doesn't exist. But if they're right, if the pulses are intentional, if something inside 3i Atlas is counting, transmitting, preparing, then the world needs to know. Just not yet. November 6th, the pulses continue. Every 11.3 hours, lasting 47 seconds, getting brighter, getting stronger. As if something out there, drifting past the sun, is waking up. As if it's been waiting for this moment. For perihelion, for the heat, for the closeness. And now, finally, it's ready. Ready to do what it came here to do. Whatever that is. November 9th, 2025, 8 days after perihelion. 3i Atlas is now moving away from the sun, accelerating outward, beginning its long journey back into the dark between stars. For most interstellar visitors, this would be the end of the show. The heat fades, activity dies down. The object grows dimmer as it retreats into the outer solar system, eventually becoming too faint to observe. But 3i Atlas isn't fading quietly. If anything, it's getting louder. And what started as a subtle anomaly, a strange pattern buried in light curves, is now becoming something impossible to ignore. Because the pulses haven't stopped. They're still there. Every 11.3 hours, lasting 47 seconds. Precise as a metronome. But now instruments are detecting something deeper. Something that shouldn't be there at all. Dr. Michael Chen sits in front of a bank of monitors at NASA's Infrared Telescope facility in Hawaii. It's just past midnight. The dome is open. The telescope tracks 3i Atlas as it drifts across the sky, invisible to the naked eye but glowing faintly in infrared wavelengths. Infrared light is heat. When you point an infrared telescope at an object, you're measuring how much thermal energy it's radiating. For comets and asteroids, that tells you about surface temperature, composition, how the object responds to sunlight. Dr. Chen has been collecting infrared data on 3i Atlas for 3 weeks, watching how its temperature changes as it swung past the sun and now moves away. Most of the readings have been predictable. The object heated up as it approached perihelion, peaked around October 15th, and is now cooling as expected. But tonight something different shows up. During one of the brightness pulses, the one that astronomers worldwide are now tracking religiously, Dr. Chen's infrared instruments detect a spike. A burst of heat. Not from the surface, from inside. He stares at the data, rewinds the observation, watches it again. The surface temperature barely changes, but deep within the nucleus, something releases a pulse of thermal energy. Brief, intense, localized. He measures the depth, runs the calculation 3 times. 52 meters below the surface, whatever is generating this heat isn't on the outside. It's buried, shielded by layers of ice and rock, protected. His hands hover over the keyboard. Because here's what he knows about comets. They're cold, inert. When they heat up, it's because sunlight warms their surfaces. The heat radiates outward. It doesn't come from within. But this is coming from the inside out. Like something deep in the core is turning on, activating, generating energy. He saves the data, tags it as priority, sends it to Dr. Vasquez with a subject line that reads, "You need to see this." Within 2 hours, 6 other astronomers are reviewing the same observation, and within a day, the infrared findings are confirmed by a second telescope in Chile. The heat pulses are real, they're internal, and they're synchronized perfectly with the optical brightness spikes. Whatever is making 3i Atlas flash brighter every 11.3 hours is also generating heat from deep inside the object. November 13th. Halfway around the world at the Arecibo Observatory in Puerto Rico. Wait. Arecibo collapsed in 2020. Let me correct that. At the Green Bank Observatory in West Virginia, radio astronomers are conducting routine sweeps of the sky, listening for signals, mapping radio sources, cataloging the faint whispers of the universe. Radio astronomy is different from optical astronomy. You're not looking at light, you're listening to electromagnetic radiation at longer wavelengths, radio waves. The same kind your phone uses, but coming from space. Most of what you hear is noise, static, the hiss of the cosmic microwave background, occasional bursts from pulsars or distant galaxies. But on November 13th, during a scheduled observation of 3i Atlas, something unusual shows up. A faint signal, structured, repeating, at 1420 megahertz. The technician monitoring the equipment almost dismisses it. Radio interference is common. Cell towers, satellites, aircraft. Earth is noisy, and filtering out human-made signals is a constant challenge. But this signal is coming from the right coordinates, from the exact position of 3i Atlas in the sky. He flags it, saves the recording, passes it to the senior astronomer on duty. Dr. Sarah Lynn reviews the data with coffee in hand, exhausted from a long shift. She's about to dismiss it as interference when she notices the frequency. 1420 megahertz. She sits up. Because 1420 megahertz is special. It's the frequency at which hydrogen atoms emit radiation. Hydrogen is the most abundant element in the universe, and this frequency, called the hydrogen line, is one of the most common signals in space. But it's also significant for another reason. It's called the water hole, a term coined decades ago by scientists involved in SETI, the search for extraterrestrial intelligence. The idea is simple. If an alien civilization wanted to send a signal that other technological species might notice, they'd broadcast near the hydrogen line. It's a universal frequency, one that any civilization studying the cosmos would know. It's where you'd expect to find a message. Dr. Lin pulls up the full recording, isolates the signal, enhances it, and there, buried in the noise, is a pattern. Faint, regular, structured. It's not random static. It's not a natural radio source like a pulsar. It's organized. She checks the timing, cross-references it with optical observations of 3i Atlas, and her breath catches. The radio bursts align with the brightness pulses, perfectly. Every time 3i Atlas flashes brighter, every 11.3 hours for 47 seconds, there's a corresponding burst of radio energy at 1420 megahertz. The two signals are locked together. She reaches for her phone, dials Dr. Vasquez's number. "Elena," she says quietly, "we need to talk." November 15th, a conference call, 15 scientists. 5 countries. They share data, overlay graphs, compare timestamps, optical pulses, infrared heat spikes, radio bursts. All 3 phenomena, detected by independent instruments, across different wavelengths separated by thousands of miles, are synchronized, phase-locked, happening at the exact same time, within margins of error so small they're almost negligible. One scientist, a professor from Caltech, speaks carefully. This level of correlation, it's not coincidental. Something is driving all 3 signals, a single source. Dr. Nakamura from Hawaii adds, and that source is deep inside the nucleus. The heat signature places it at least 50 meters below the surface. Silence. Because everyone on the call understands what this means. Surface phenomena, outgassing, ice sublimation, those things are chaotic. Influenced by sunlight, by rotation, by surface irregularities. But something 50 meters deep? That's isolated, shielded, independent of external conditions. That's not reacting to the environment. That's operating on its own. Dr. Ramirez from Chile speaks next. Her voice is steady, but there's an edge to it. We need to consider the possibility that this object contains something functional, a mechanism, a device. No one argues, no one dismisses it. They just sit there staring at their screens, processing the implications. Dr. Lin from Green Bank breaks the silence. There's something else. The intervals are changing. Everyone looks up. What do you mean? Dr. Vasquez asks. Dr. Lin pulls up a graph, shares her screen. I've been measuring the time between pulses. At first they were exactly 11.3 hours apart, but over the last week the interval has been decreasing. Slowly, consistently, she highlights the data points. October 25th, 3,000 hours between pulses. November 1st, 11,2997 hours. November 8th, 11,2991 hours. November 15th, 11,2985 hours. The change is tiny, fractions of a second, but it's real, measurable, and it's not random. It's decreasing by about 0.3 seconds per orbit, Dr. Lin says. Like clockwork. Dr. Chen leans forward. Wait, per orbit? You mean every time it completes one rotation? No, Dr. Lin corrects. Per orbit around the sun, every time it completes one lap, the interval between pulses shortens by 0.3 seconds. Dr. Vasquez processes this. But it's moving away from the sun now. It's past perihelion. If this were thermally driven, if sunlight were causing the pulses, they'd be slowing down as the object cools, not speeding up. Exactly, Dr. Lin says quietly. The implications settle over the group like a weight. Because this pattern, this gradual acceleration of the signal, doesn't fit any natural explanation. It's not rotation. Objects don't speed up their spin as they move away from the sun. They slow down. It's not outgassing. That's erratic, unpredictable. It doesn't follow orbital mechanics with this kind of precision. This is something else, something that's responding to the object's position, to its trajectory, to its distance from the sun, as if it's calibrated, programmed, as if it's counting down. Dr. Nakamura asks the question everyone's thinking. What happens when the interval reaches zero? No one answers, because no one knows. Maybe nothing. Maybe the pulses just stabilize. Maybe whatever mechanism is driving this reaches some equilibrium and continues indefinitely. Or maybe zero is the endpoint, the moment when the signal finishes, when the message completes, when whatever 3i Atlas came here to do is done. November 18th. The data is now undeniable. The correlation is published in a private preprint, shared only among a select group of researchers. No press, no public announcement, not yet. But the whispers are spreading. Astronomers talk. They email. They share observations on private forums. And slowly, carefully, the question starts to circulate through the scientific community. Is 3i Atlas artificial? Most scientists still resist the idea. It's too big, too bold, too paradigm-shattering. They look for alternatives, natural explanations, exotic but plausible mechanisms. Maybe the object has a core of radioactive material, heating from within, creating the thermal pulses. But radioactive decay is random. It doesn't pulse on a schedule. Maybe there's a subsurface ocean, liquid water or ammonia, sloshing around as the object rotates, creating pressure waves that affect surface brightness. But liquids don't stay liquid at interstellar temperatures, and pressure waves don't generate radio signals. Maybe the object is magnetically active, its internal field interacting with the solar wind, creating the observed phenomena. But comets aren't magnetic. Not like this. Not with this precision. Every explanation, no matter how creative, hits the same wall. It doesn't account for the synchronization. The phase locking. The decreasing intervals. It doesn't explain why three independent signals, operating across different physics, different wavelengths, different detection methods, are all moving in perfect harmony. Dr. Vasquez sits alone in her office late one night. The building is empty. The only sound is the hum of the ventilation system. On her screen, she's overlaid all the data: optical, infrared, radio. The graphs line up like layers of music. 3 instruments playing the same note, the same rhythm, the same song. She thinks about Oumuamua, how it accelerated without a visible explanation, how scientists debated for years whether it was outgassing or something else. She thinks about 2i Borisov, how it was easier, explainable. A comet from another star, but still just a comet. And now, 3i Atlas, not random, not chaotic, organized, purposeful, precise. She opens a new document, starts typing. Not a formal paper, just thoughts, observations, questions. What if, she writes, we're not observing a natural object? What if 3i Atlas is a probe, a messenger, a device sent from another star system designed to activate when it passes close to a sun? She pauses, reads what she's written, deletes it. Too bold, too speculative. But the thought remains. Because everything they're seeing, every measurement, every correlation, every anomaly, fits that hypothesis. Not perfectly, not without questions, but better than any natural explanation they've tried. She closes the document without saving, leans back in her chair, stares at the ceiling, and wonders if somewhere out there, light years away, someone is listening, waiting for confirmation that their signal was received, that after traveling for millennia through the cold and dark, their messenger finally arrived. And that we noticed. November 20th. The pulses continue. Every 11-28 hours now, still decreasing, still precise. The radio bursts grow slightly stronger, the thermal spikes slightly more intense, and deep within the nucleus of 3I Atlas, 50 meters below the frozen surface, something keeps transmitting, counting, broadcasting, reaching out, to us, or to something else. We don't know yet, but we're listening now. And whatever message it's sending, we're starting to hear it. November 21st, 2025. At the Massachusetts Institute of Technology, in a windowless office filled with whiteboards covered in equations, Dr. Amanda Fisher stares at her computer screen. She's been awake for 36 hours. Empty coffee cups line her desk. Her eyes burn, but she can't stop looking at the numbers, because what started as a simple orbital mechanics calculation has turned into something else entirely, something that's making her question everything she thought she knew about chance and coincidence. Dr. Fisher is an astrodynamicist. She studies how objects move through space, trajectories, orbits, the elegant mathematics that governs how planets, comets, and asteroids dance around the sun. She's calculated thousands of orbits in her career, mapped the paths of near-Earth asteroids, predicted when comets would return, designed spacecraft trajectories for NASA missions. She knows what random looks like, and this isn't random. 3 weeks ago, after the news broke about the synchronized signals, about the pulses and the radio bursts, Dr. Fisher became curious. She wanted to understand 3I Atlas's trajectory, where it came from, how it entered the solar system, what path it took through our neighborhood. Standard questions, routine analysis. But as she ran the calculations, as she mapped the object's orbit in three-dimensional space, something started bothering her. The trajectory was convenient. Too convenient. So she dug deeper, pulled more data, ran more simulations, and what she found made her stop sleeping. She calls her colleague, Dr. James Park, at 2 in the morning. He answers groggily. "Amanda, what's wrong?" "I need you to check something," she says. Her voice is tight, controlled. "I need you to verify my calculations because if I'm right, if these numbers are correct..." "Slow down," Dr. Park says, suddenly awake. "What are you talking about?" 3I Atlas, its trajectory, the angle it entered the solar system, the timing. "James, it's not random. It can't be." Silence on the line. Then, "I'll be there in 20 minutes. By dawn, they've both run the analysis independently. Different software, different methods, same result. Dr. Park sits back, rubbing his face. "Okay, walk me through it." Dr. Fisher pulls up a 3D model of the solar system on her screen. Here's 3I Atlas entering from interstellar space. She traces its path with her cursor. It comes in from this direction, moving at about 26 kilometers per second. Dr. Park nods. "Standard hyperbolic approach." "Right, but look at the angle." She rotates the model. It enters almost perpendicular to the ecliptic plane. That's the flat disk where all the planets orbit. Most objects in our solar system stay close to this plane, but interstellar objects can come from any direction, any angle. Sure, random arrival angles. Except this one crosses the ecliptic plane at a very specific point. She zooms in. Right here, at 1.2 astronomical units from the sun, and it crosses exactly when Earth is positioned. She highlights Earth's orbit. Here. Dr. Park stares at the screen. In direct line of sight. Exactly. When 3I Atlas passed through the ecliptic plane, Earth was perfectly positioned to observe it. Not behind the sun, not on the far side of our orbit, right there, where our telescopes could see it clearly. Dr. Park frowns. That's interesting, but it could still be coincidence. Could be, Dr. Fisher agrees. So I checked the timing. 3I Atlas reached perihelion on October 15th. Late October. Northern Hemisphere autumn. So that's when observing conditions are optimal in the Northern Hemisphere. Clear skies, cooler weather, less atmospheric turbulence. Most of our major observatories, Hawaii, Chile, the Canaries, all had perfect viewing conditions during its closest approach. Dr. Park is quiet now, listening. Dr. Fisher continues. And here's the thing. If 3I Atlas had arrived 6 months earlier or later, if it had reached perihelion during northern summer or winter, observing conditions would have been worse. Weather, atmospheric interference, seasonal positioning. She pulls up. Another graph. But it didn't arrive 6 months earlier or later. It arrived exactly when the skies were clearest, when our telescopes were most active, when we had the best chance of seeing it. Dr. Park stares at the data. What are the odds? Dr. Fisher takes a breath. I ran the simulation 10,000 times. I randomized the arrival angle, the timing, the trajectory. And I asked, how many random interstellar objects would enter the solar system with geometry this favorable for Earth-based observation? She pulls up the results. 1 in 12,000. The number sits between them. Heavy. Undeniable. Dr. Park speaks carefully. That's statistically significant. That's an understatement, Dr. Fisher says. James, this object entered our solar system at the perfect angle, at the perfect time, with the perfect trajectory to maximize its visibility from Earth. Not from Mars, not from Jupiter. From Earth, specifically. You're saying it was planned. I'm saying the probability that this is random is less than 0.01%. They spend the next 3 days writing the paper, checking the math, verifying every assumption, making sure there are no errors, because they know what this implies, and they know how the scientific community will react. On November 24th, they upload the preprint to Archive, the online repository where researchers share findings before peer review. The title is carefully worded, Orbital Analysis of 3I Atlas, Geometric Considerations for Enhanced Terrestrial Observability. Dry, academic, safe, but the abstract is clear enough. Our analysis suggests that 3I Atlas's trajectory through the inner solar system exhibits geometric properties that significantly enhance its observability from Earth during optimal viewing conditions. The probability of such a trajectory occurring by chance is calculated at less than 0.083, or approximately 1 in 12,000. While natural explanations remain possible, the statistical improbability warrants consideration of alternative scenarios. Translation: this object's path is too perfect to be an accident. The preprint goes live at 9 a.m. Eastern Time. By noon, it's been downloaded 6,000 times. By evening, it's the most viewed paper on Archive that week. And by the next morning, the emails start flooding in. Some scientists are supportive, excited. They've been thinking the same thing privately, and now there's mathematical backing. Others are skeptical, cautious. They point out that improbable doesn't mean impossible. That 1 in 12,000 odds still means it could happen naturally, and some are outright hostile. You're feeding conspiracy theories, one email reads. Irresponsible speculation, says another. This will damage the credibility of the entire field, a senior researcher. Warns. Dr. Fisher reads them all. Doesn't respond. Just keeps checking the data. Making sure she didn't miss anything. Because she knows what she's claiming. And she knows the weight it carries. But the numbers don't lie. And every time she runs the simulation, every time she checks the geometry, the conclusion is the same. 3I Atlas's trajectory is optimized, as if someone plotted the course, calculated the angles, timed the arrival, as if this object was sent here deliberately, to be seen, to be noticed. Dr. Vasquez calls her on November 26th. I read your paper, Dr. Vasquez says quietly. And I think you're right. Dr. Fisher closes her eyes. Relief washes over her. Because Dr. Vasquez's opinion matters. She's respected, careful. Not given to wild speculation. There's something else, Dr. Vasquez continues. Something I've been thinking about. If this object was sent here intentionally, if it was designed to be observed, then the signals make sense. How so? It's using the sun. Dr. Vasquez's voice is thoughtful, measured. Think about it. 3I Atlas comes in from interstellar space, cold, dormant, but as it approaches the sun, as it heats up, as it reaches perihelion, the signals start, the pulses, the radio bursts, the thermal emissions. Dr. Fisher sees where she's going. It's using solar energy. Not just energy, the sun's gravity too. It's using the gravitational slingshot not just to accelerate, but to broadcast, to amplify. The closer it gets, the stronger the signal becomes. Dr. Fisher thinks about this, like a spacecraft using a planetary flyby. But instead of gaining speed, it's gaining... what? Broadcasting power? Maybe. Or maybe it's just the optimal moment. The moment when it's closest to us. When the signal has the shortest distance to travel. When we're most likely to be watching. A transmission window. Exactly. They sit in silence for a moment, processing the implications. Dr. Fisher speaks first. Elena, if we're right, if this thing was sent here deliberately to be observed, to broadcast a signal during perihelion, then someone somewhere wanted us to see it, Dr. Vasquez finishes. Wanted us to notice. Wanted us to receive whatever message it's sending. Or they wanted someone to receive it. Maybe not us specifically, maybe just whoever's here, whoever's watching. Another pause. That's a terrifying thought, Dr. Vasquez says quietly. Which part? All of it. By early December, the scientific community is fracturing. Some researchers embrace the artificial hypothesis. They cite the trajectory analysis, the synchronized signals, the decreasing pulse intervals. They argue that the evidence, while not conclusive, is compelling enough to take seriously. Others push back hard. They insist on natural explanations, argue that improbable events happen all the time, that 1 in 12,000 odds aren't good enough to invoke alien technology. The debate spills into conferences, journal articles, social media. Astronomers who've worked together for decades find themselves on opposite sides, because this isn't just about one object, it's about worldview. It's about whether we're alone. And that question changes everything. Dr. Park sits with Dr. Fisher in her office one evening. Outside, snow falls softly over Cambridge. The campus is quiet. Finals are over. Students have gone home for the holidays. "Do you regret publishing?" he asks. Dr. Fisher looks at him. "No. The data is sound. The analysis is correct. We didn't sensationalize it. We just reported what we found. But people are treating it like proof. That's not our fault. We were clear. We said coincidence is still possible. We gave the exact probability. And what do you think? Honestly, not as a scientist, as a person, do you think it's artificial?" Dr. Fisher is quiet for a long time. Then, "I think the universe is stranger than we imagine. I think there are phenomena out there we don't understand. Natural processes that can create patterns and precision we associate with design." "That's not an answer." "I know." She looks out the window, watches the snow fall. "But if you asked me to bet," she says slowly, "if you made me choose, I'd say yes. I think someone sent this. I think 3i Atlas is a probe, a messenger, something designed to announce its presence, to make sure we notice." "Why?" "I don't know. Maybe to see if anyone's home. Maybe to deliver a message. Maybe just to say, we're here. We exist. We're reaching out." She turns back to him. "And if that's true, if this object traveled for millions of years through the empty dark just to pass through our solar system at exactly the right moment, at exactly the right angle." She trails off. Dr. Park finishes the thought. "Then we're not alone. And we never were." December 3rd. The pulses continue. Every 11:27 hours now. Still decreasing, still precise. The signals grow stronger, the intervals shrink, and somewhere deep within the frozen nucleus of 3i Atlas, 50 meters below the surface, something continues transmitting. Using the sun's energy, the sun's gravity, the perfect geometry of its trajectory, broadcasting, reaching out, to us. And now finally, after months of data and debate and discovery, we're starting to understand, not what it's saying, not yet, but that it's saying something. That this object, this visitor from another star, didn't arrive by accident. It came here with purpose, with intent, and that changes everything. Because if the geometry is right, if the trajectory was calculated, if the timing was chosen, then someone, somewhere, is waiting. Waiting for us to answer. Waiting to see if we understand. Waiting to know if we're ready. For what comes next? November 28th, 2025. The world is watching now. Not just astronomers, not just scientists. Everyone. Because the story has broken. Leaked through academic circles, through private emails, through whispered conversations that became forum posts, that became articles, that became headlines. Interstellar object shows. Signs of artificial origin. Is 3i Atlas a probe from another civilization? Scientists debate. Are we being contacted? The news cycles endlessly. Cable networks bring on experts. Talking heads debate. Social media explodes with speculation, theories, fear, hope, everything in between. And in the middle of it all, the scientists who started this, the ones who noticed the anomalies and ran the calculations and published the data, they sit quietly, watching, waiting. Because they don't have answers yet. Just questions. Questions that are getting harder to ignore. The Vatican issues a statement on November 26th. It's brief, carefully worded. The kind of statement that's been reviewed by committees, edited by theologians, approved at the highest levels. The Church has always recognized that God's creation extends far beyond our world. The discovery of phenomena that challenge our understanding is not a challenge to faith, but an invitation to deeper wonder. We await scientific clarity on the nature of 3i Atlas while affirming that all truth, wherever it is found, comes from the Creator. It's diplomatic, open-ended, reassuring to believers while not committing to any specific interpretation. But the fact that the Vatican felt the need to issue a statement at all, that tells you something. Religious leaders across the world follow suit. Imams, rabbis, Buddhist monks, Hindu scholars, each offering their perspective, each trying to make sense of what this might mean for their understanding of existence, creation, the universe. Most strike a similar tone, calm, measured, not afraid, but processing. Because if Three-Eye Atlas is artificial, if we're truly not alone, every religion on Earth will have to reconcile that reality with their teachings. And that's not a small thing. Governments, on the other hand, stay silent. No official statements from NASA, no press conferences from the European Space Agency, no comments from Russia, China, India, any of the spacefaring nations. Publicly, they say nothing. Privately, well, that's harder to know. But people notice the silence, and in that silence, speculation grows. Online forums explode. Reddit threads with thousands of comments. Twitter debates that trend for days. YouTube videos, analyzing every piece of data, every graph, every statement from scientists. Some people are excited, hopeful. They see this as proof we're not alone, that life exists beyond Earth, that maybe, just maybe, we're about to make contact with something greater than ourselves. Others are terrified. They talk about invasion, about threats, about unknown intentions and worst-case scenarios. And some just don't believe it. They call it a hoax, a mistake, misinterpreted data, scientists seeing patterns where none exist. They point to past false alarms, past claims that turned out to be nothing. Remember the phosphine on Venus, they say? Remember the wow signal? This will be the same. Natural explanation incoming. Maybe they're right. Maybe this will all collapse under scrutiny. Maybe a mundane explanation will emerge that accounts for everything. But as November turns toward December, as more data comes in, as the signals continue, that explanation hasn't appeared yet, and the weight of the question grows heavier. The scientific community fractures, not publicly, not dramatically, but the cracks are there, visible if you know where to look, in conference rooms, in email chains, in private conversations over coffee or wine or late-night phone calls. Some astronomers embrace the artificial hypothesis, not recklessly, not without skepticism, but they look at the evidence, the trajectory, the signals, the synchronization, and they say, this warrants serious consideration. They point to the MIT paper, to the 1 in 12,000 odds, to the phase-locked pulses, to the decreasing intervals. We have to follow the data, they argue, and the data is pointing somewhere uncomfortable. Others push back just as hard. They're not being stubborn, they're being careful, scientific. They know how easy it is to see patterns in noise, to leap to conclusions, to let excitement override rigor. Extraordinary claims require extraordinary evidence, they say. Quoting Carl Sagan, reminding everyone that jumping to aliens is the last resort, not the first. They look for natural explanations, exotic but plausible mechanisms, unusual chemistry, rare phenomena we haven't fully documented yet. Just because we don't understand it doesn't mean it's artificial, they argue. The universe is full of things we don't understand. Both sides have valid points. Both sides are scientists, trained in the same methods, looking at the same data. But they're reaching different conclusions. And that divide, it's starting to hurt. Colleagues who've worked together for years find themselves on opposite sides. Friendships strain, collaborations pause. Not because anyone is being unreasonable, but because the stakes are so high. Because if one side is right and the other is wrong, the implications are enormous. Dr. Vasquez attends a conference in early December, a small gathering, invitation only, just 50 astronomers, meeting in person to discuss Three-Eye Atlas, away from media, away from public scrutiny. The first day is tense, presentations are given, data is shared, arguments are made. By evening the room is divided. Not evenly, maybe 60-40. Most still leaning toward caution, toward natural explanations, but a significant minority willing to consider alternatives. During a break, Dr. Vasquez stands outside, looking up at the stars. The conference center is in the mountains, dark skies, no light pollution. A colleague joins her, someone she's known for 15 years, published papers with, shared telescope time with. Elena, he says quietly. You really think it's artificial? She doesn't answer right away. I think, she says carefully, that we're looking at something unprecedented, and I think we owe it to ourselves, to humanity, to consider all possibilities, even the uncomfortable ones. But you don't have proof. No, I don't. Then why push this? Why risk your reputation on speculation? She looks at him. Because what if we're wrong to be cautious? What if this is exactly what it looks like, and we're so afraid of being fooled that we miss the most important discovery in human history? He doesn't have an answer for that. They stand in silence, looking up. Somewhere out there, Three-Eye Atlas continues its journey, moving away from the sun, growing dimmer, but still pulsing. Still transmitting. Still something. And then on December 2nd, everything shifts again. A postdoctoral researcher at Caltech, a young woman named Dr. Maya Ose, is doing something routine, mundane even. She's mining archived data from the Hubble Space Telescope. Hubble has been observing the universe for over 30 years. It's taken millions of images. Most of that data is publicly available, sitting in databases, waiting for anyone who wants to analyze it. Dr. Ose is studying distant galaxies, looking for supernovae, standard research. But while searching through 2023 observations, she notices something odd. An infrared signature, faint, almost imperceptible, in a region of space that should be empty. She almost dismisses it. Probably an artifact. A cosmic ray hit. Something that fooled the detector. But something makes her check the coordinates, and her heart stops. The signature is in the exact region of space where 3i Atlas came from. She checks the date, May 17th, 2023. 2 years before 3i Atlas was discovered. 2 years before anyone knew it existed. She pulls up current trajectory data for 3i Atlas, runs the orbit backward, calculates where the object would have been in May 2023. The position matches. Whatever Hubble detected, it was 3i Atlas. But the object was still years away from the inner solar system, still in deep space, cold, dark, inactive. It shouldn't have shown any infrared signature at all, unless something was already active, already generating heat, already there. Dr. Ose sends the finding to Dr. Vasquez at 3 a.m. Subject line: "You need to see this immediately." Dr. Vasquez opens the email, reads it 3 times. Then she calls Dr. Nakamura, Dr. Ramirez, Dr. Chen, everyone who's been tracking 3i Atlas. Within 12 hours, a dozen scientists are analyzing the archived Hubble data. They enhance the image, isolate the signature, measure the intensity. It's weak, very weak, but it's there. An infrared glow, coming from a point in space where 3i Atlas sits, years before anyone on Earth knew to look. Dr. Chen runs thermal calculations. If this is real, if the object was emitting detectable infrared radiation in 2023, he trails off. Dr. Vasquez finishes the thought. Then it was active long before perihelion, long before solar heating could explain it. Which means the heat isn't coming from the sun. Silence. Because that changes everything. Every natural explanation for the thermal emissions, for the pulses, for the activity, relied on solar heating. On the object warming up as it approached the sun, triggering sublimation and outgassing. But if it was already warm in 2023, if something inside was already generating energy years before perihelion, then the sun isn't the power source. Something else is. Something internal. Something that's been running for at least 2 years, probably longer. Something that doesn't need external energy. The discovery leaks within days. Hubble images show 3i Atlas was active years before discovery. Object was waiting in deep space, data suggests. Infrared signature detected in 2023 raises new questions. The scientific community reels. Because this isn't speculation anymore. This isn't interpretation of ambiguous data. This is archived observation. From Hubble, one of the most reliable instruments humanity has ever built, and it shows that 3i Atlas was doing something, emitting something, while still in the outer solar system, where nothing should be happening. Dr. Vasquez sits in her office and staring at the enhanced Hubble image, the faint glow, the infrared signature. 2 years ago, when nobody was watching, when the object was just another invisible speck in the vast darkness. It was already active, already awake. The word comes to her unbidden, unwelcome but accurate, as if 3i Atlas entered the solar system not dormant but aware, not passive but prepared, as if it had been waiting, watching, measuring the distance, calculating the approach, preparing for perihelion, for the moment when it would be closest, when we would be watching, when the signal could be sent. By mid-December, the question is no longer whether 3i Atlas is unusual. Everyone agrees it's unusual. The question is what unusual means. Natural but unprecedented? A phenomenon we've never encountered before but that fits within known physics? Or something else? Something designed? Something sent? And if sent, by whom? And why? Those questions hang over everything now. Over every conversation, every news broadcast, every late-night thought. Humanity stands at a threshold. On one side, the universe we thought we knew. Vast, empty, quiet, with life rare and scattered and unlikely to meet. On the other side, something different. A universe where we're not alone, where others exist, where messages travel between stars, where civilizations reach out, hoping to find someone listening. We don't know which side we're on yet. The data isn't conclusive. The evidence, while compelling, isn't definitive. But the weight of it all, the accumulated anomalies, the statistical improbabilities, the archived observations, it's heavy. Heavy enough that even the skeptics are starting to feel it. Heavy enough that the silence from governments feels less like caution and more like preparation. For what? Nobody will say. But something is shifting. In observatories, in government offices, in the collective consciousness of humanity. The question is no longer, could this be artificial? The question is becoming, what do we do if it is? And nobody has that answer yet. December 8th. The pulses continue, every 11:25 hours now. Still shrinking, still precise. The signal grows stronger, the intervals decrease, and deep in the frozen nucleus of 3i Atlas, whatever has been transmitting since at least 2023, probably longer, keeps broadcasting. Counting down, reaching the end of whatever sequence it was programmed to complete. We're listening now. Not just scientists, the whole world. Listening, watching, waiting. For the signal to resolve, for the message to clarify, for the answer to reveal itself. And somewhere, light years away, in a place we can't see and don't know, someone might be listening too, waiting for confirmation that their message was received, that after traveling for millennia through the cold and dark, it finally arrived. November 9th, 2025. 11:47 p.m. Pacific Time. Right now. 3i Atlas is moving past Mars, accelerating outward, heading back toward the darkness it came from. The pulses continue. Every 11:23 hours now. The intervals have been shrinking steadily for weeks, like a clock winding down, approaching some final moment. And tonight, around the world, astronomers are waiting. Because the pattern suggests something is coming. Something soon. Dr. Vasquez sits in the control room at Mauna Kea, watching the live feed from the telescope. Around her, monitors glow softly in the darkness. Outside, through the dome opening, stars fill the sky from horizon to horizon. She hasn't slept more than a few hours in the past week. None of them have, because they all feel it. The sense that this is building toward something, that whatever 3i Atlas came here to do. It's almost finished. The next pulse is due in 17 minutes. She checks the other feeds. Observatories in Chile, South Africa, Spain, all tracking the same object, all waiting. Amateur astronomers too. Thousands of them. People with backyard telescopes, cameras mounted on tripods, watching the same patch of sky, waiting for the light. At 11:58 p.m., someone in the control room speaks quietly. 5 minutes. Dr. Vasquez pulls up the light curve display. The graph showing brightness over time. The last pulse 11 hours ago was the strongest yet. A spike in brightness that lasted the usual 47 seconds but climbed higher than any previous pulse, as if the signal is crescendoing, building toward something. 2 minutes, another voice says. The room is silent except for the hum of equipment, the soft clicks of cameras adjusting, the whisper of ventilation. Outside, 3i Atlas is invisible to the naked eye, too faint, too far away. But the instruments can see it, tracking, measuring, recording. 1 minute. Dr. Vasquez leans forward. Her hands grip the edge of the desk. Around the world, in control rooms and observatories and backyard setups, thousands of people watch their screens, holding their breath. 30 seconds. The light curve on Dr. Vasquez's monitor is flat, steady, the baseline brightness of 3i Atlas as it reflects sunlight. 10 seconds, nothing yet. 5, 4, 3. And then, the line spikes, not gradually, not smoothly. It jumps. The brightness of 3i Atlas surges, doubles, triples, climbing higher than it's ever been. The pulse that should last 47 seconds keeps going. 50 seconds, 60 seconds, 90 seconds. What's happening? Someone asks. Dr. Vasquez doesn't answer. She's staring at the monitor, at the graph climbing higher and higher. The object is flaring, brightening to levels that don't make sense. That can't be explained by reflection or rotation or any natural process. It's like someone turned up the volume, like 3i Atlas is shouting. One final transmission before what? The pulse holds at peak brightness for another 30 seconds, steady, unwavering, and then slowly it begins to fade, dropping back down, returning to baseline. The whole event lasts 2 minutes and 18 seconds, nearly 3 times longer than any previous pulse, and far brighter. Dr. Vasquez looks at the timestamp. 12:04 a.m. Pacific. November 12th now. 03:04 UTC. She makes a note, saves the data, and waits. Because according to the pattern, the next pulse should come in just over 11 hours, but something tells her it won't. Something tells her that was the last one. That night. Early morning hours, UTC. Evening in Hawaii, where Dr. Vasquez is still awake, still watching. The time for the next. Pulse arrives, and nothing happens. The light curve stays flat. No spike, no brightening, no pulse. Just baseline. She waits. Maybe it's late. Maybe the interval changed. Maybe. But 5 minutes pass. 10 minutes. 20. Nothing. She pulls up the radio telescope data. Checks Greenbank, observatories in Australia, stations across the globe. No radio bursts. No signal at 1420 markers. No structured noise. Silence. She checks the infrared feed from NASA's telescope. No thermal spikes. No heat pulses from the nucleus. The temperature is dropping. Cooling. The internal heat source on it, whatever it was, is gone. Vanished. As if someone flipped a switch. Dr. Vasquez sits back in her chair, stares at the monitors. Around the world, other astronomers are seeing the same thing. The signal has stopped. After months of perfect regularity, after weeks of decreasing intervals, after that final powerful burst the night before, 3I Atlas has gone silent. The first reaction is confusion. Maybe it's a gap, a pause in the transmission. Maybe the signal will resume in another 11 hours, or 12, or 24. But hours pass, and the silence continues. No pulses, no radio bursts, no thermal anomalies. The object continues moving outward, growing fainter, but otherwise, nothing. It's dormant again, inert, like it was when it first entered the solar system months ago, as if whatever animated it has switched off. Completed its task, finished its mission. Less than a day after the signal stopped, Dr. Nakamura notices something else. He's reviewing astrometric data, precise measurements of 3I Atlas's position over time when he sees it. The object is tumbling, not spinning smoothly like it was before, not rotating on a stable axis. It's tumbling, chaotically, end over end, its orientation changing unpredictably. He runs the analysis again, checks the data, confirms it with observations from Chile. The tumbling is real, and it started right after the signal stopped. He sends the finding to Dr. Vasquez. She reads the email, closes her eyes. Because a stable spin means structure. It means the object has a well-defined axis, a balanced distribution of mass. It means something is maintaining that stability. But tumbling? Tumbling means something changed. Something inside the object shifted, or stopped working. Like a spacecraft losing its guidance system. Like a satellite whose stabilizers failed. Like a probe that completed its mission and shut down. Dr. Vasquez pulls up the old data, the light curves from when 3I Atlas first entered the system. Back then the rotation was smooth, stable, regular, and now? Now it's chaos. As if whatever kept the object oriented, whatever maintained its spin, is no longer functioning, or no longer needed. Days later, the scientific community is grappling with what this means. The signal stopped, the heat source vanished, the stable rotation collapsed into tumbling. All at once, all within hours of each other. Some scientists argue this supports the natural hypothesis. Maybe the object's volatile ices finally ran out. Maybe the thermal activity was just outgassing that depleted its fuel. Maybe the tumbling is just a normal evolution of rotational state. But others point out the timing. The signal didn't fade gradually. It stopped abruptly, precisely, at a specific moment. The thermal emissions didn't decline slowly, they vanished, instantly. And the tumbling began immediately afterward, as if systems shut down, as if power was cut, as if something finished what it came here to do. Soon after, Dr. Vasquez attends a hastily organized video conference. 20 astronomers, emergency meeting, everyone trying to make sense of what just happened. So it's over? Someone asks. The phenomenon, whatever it was, has ended? It appears so, Dr. Nakamura confirms. We've had days of continuous observation with no activity. No pulses, no thermal anomalies, no radio signals. And the tumbling? Confirmed by multiple observatories. The object has lost rotational stability. Silence on the call. Dr. Fisher from MIT speaks carefully. The timing is significant. The signal ends, the heat source stops, the rotation destabilizes, all within the same narrow window. What are you suggesting? Someone challenges. I'm suggesting that these events are connected, that they all stem from a single cause. Something inside 3I Atlas that was operating, maintaining stability, generating energy, broadcasting, and then stopped. Ran out of power? Completed its program, Dr. Vasquez says quietly. Everyone looks at her through their screens. What if, she continues, this object came here to do something specific, to reach perihelion, to broadcast during its closest approach, to transmit whatever data or signal it carried. And once that was done, once the mission was complete, it shut down. You're describing a probe, someone says flatly. I'm describing what the data shows. The call grows tense, defensive. Some people push back, insisting on natural explanations. Others nod slowly, acknowledging what they've all been thinking privately. The debate continues for hours. No consensus is reached, but everyone agrees on one thing. Something extraordinary just happened, and it's now over. In the days that follow, the world is processing. News outlets report that the 3i Atlas signal has stopped. Scientists give interviews, carefully hedging their language. Unusual phenomenon. Unprecedented observations. Further study needed. Nobody says alien probe on camera, but everyone's thinking it. Online, the speculation explodes. Forums, social media, YouTube videos analyzing every piece of data. Some people are convinced it was artificial. Others insist it was natural. Arguments rage, but slowly, gradually, the intensity fades. Because there's no smoking gun, no decoded message, no clear proof either way. Just data, observations, anomalies that don't quite fit. And now that the signal has stopped, now that 3i Atlas is tumbling silently into the outer solar system, the story is ending. Without resolution, without answers, just questions. One evening, not long after, Dr. Vasquez sits alone in her office. The building is quiet. Most people have gone home. On her screen, she has the complete dataset open. Every observation from discovery to now. The light curves, the thermal readings, the radio bursts, the trajectory analysis. Months of data, hundreds of observations, thousands of measurements. And somewhere in all of that information, maybe there's a message. Maybe 3i Atlas carried data encoded in its pulses. In the timing, in the wavelengths, in the correlations between optical and radio and thermal emissions. Maybe it's there, waiting to be decoded, or maybe it's not. Maybe the anomalies were natural, rare, unprecedented, but ultimately just physics we don't fully understand yet. She'll never know for certain. None of them will. Because 3i Atlas didn't leave a simple message. It didn't broadcast hello in binary. It didn't spell out instructions or coordinates or equations. It just pulsed and then stopped. And now it's leaving, taking its secrets with it. She thinks about the Hubble data, the infrared signature from years ago, the evidence that this object was active, generating heat, long before anyone knew to look, as if it entered the solar system already awake, already operational, already aware. She thinks about the trajectory, the perfect geometry that placed it in Earth's line of sight during optimal viewing conditions, 1 in 12,000 odds. She thinks about the synchronized signals, optical, radio, thermal, all phase-locked, all moving together like instruments in an orchestra. She thinks about the final burst, the crescendo, the 2-minute-long pulse that was brighter than anything before it, as if 3i Atlas was making sure we noticed, making sure we recorded it, making sure we knew. And then, silence. Shut down, mission complete. Dr. Vasquez closes the data files, shuts down her computer, sits in the darkness of her office, and thinks about the universe, about how vast it is, how old, how full of possibilities, about the billions of stars, the trillions of planets, the unfathomable distances between them, and about the fact that in all that vastness, in all that emptiness, we might not be alone, that someone else might be out there, building, exploring, sending messages across the void, messages that take millions of years to arrive, messages that might pass unnoticed, unrecognized, misunderstood, but messages nonetheless, attempts at connection, at contact, at saying, we're here, we exist, we reached out. And maybe, just maybe, 3i Atlas was one of those messages. A probe sent by someone somewhere long ago, programmed to visit stars, to look for life, to transmit its findings. And maybe we were observed, cataloged, noted. Maybe right now, light years away, someone is receiving data, learning that Sol has planets, that the third one is inhabited, that someone is here, watching the sky, or maybe not. Maybe 3i Atlas was just a rock, a comet with weird chemistry, a natural object that happened to do unusual things. We'll probably never know for certain, but we'll keep watching the sky. Keep building better telescopes, keep listening for signals, keep searching, because now we know it's possible, that visitors can come from other stars, that the darkness between suns isn't empty, that maybe someday another object will arrive, and maybe next time, we'll be ready to understand. Now, as evening falls and stars begin to appear, above the atmosphere, above the clouds, beyond our world. 3i Atlas tumbles silently through the void, carrying its secrets, carrying whatever truth it held, moving away from our sun, away from our world, away from the brief moment when we almost understood, almost knew, almost touched something greater than ourselves. The echo of its signal remains, recorded, archived, preserved, but unanswered, because we don't know what it said. We don't know what it meant. We don't know if anyone was listening from the other direction. All we know is that for months, something extraordinary passed through our solar system. Something that challenged our understanding, that pushed the boundaries of what we thought possible, that made us question whether we're alone. And then, just days ago, it went silent, leaving us with data, with questions, with wonder, and with the profound, unsettling, beautiful possibility that we're not the only ones looking up at the stars, that someone else is out there too, watching, waiting, reaching out across the impossible distance, hoping that someday, somehow, we'll answer. 3i Atlas continues its journey outward, tumbling silently through the darkness. It is now moving beyond Mars, growing fainter each day. In the years to come, it will pass Jupiter, then Neptune, eventually leaving our solar system forever. Whether it carried a message and what that message might have been remains one of the greatest unanswered questions of our time. We are still watching, still listening, still hoping, and maybe someday another visitor will come, and we'll be ready.